Sometimes the best way to learn electronics is by picking apart a bad circuit. That's exactly what we're doing today with exercise 2.29 from the Art of Electronics. It features a badly biased common emitter amplifier, and we'll be breaking it down step by step, looking at its input impedance, gain, how it heads into saturation with a little bit of temperature rise. But before we do all of that, a quick word from the sponsor of this video, PCBWay. I highly recommend PCBWay. They make ordering prototypes and assembled boards fast, affordable, and hassle-free. So whether you're just testing your very first design or scaling up to full production runs, PCBWay offers a wide range of options to fit your needs. They're easy to use online platforms, let you upload your Gerber files, select your board specification, and get an instant quote. Plus, they provide excellent customer support to help you through the process. I've used PCBWay myself for many projects, and their quality and turnaround times are impressive. Big thanks to PCBWay for sponsoring this video and supporting makers like us. Now let's get started with the video. So exercise 2.29 says, disregarding the lessons of this chapter, a disgruntled student builds the amplifier shown in figure 2.97, which is this amplifier circuit over here. He adjusts the R until the quiescent point is at 0.5 VCC. So this point over here is 0.5 VCC, which is basically 10 volts. And the question itself is split into three parts. For part A, we need to calculate the input impedance. For part B, we need to calculate the small signal voltage gain. And for part C, we need to work out a temperature rise which will cause the transistor to saturate. So let's start with part A, the input impedance. Now for this question, we are looking at frequencies where C is basically a very low value impedance. So we can ignore what C is. We have some signal coming in. C is a short circuit. We have a resistor that goes to plus 20. We have a resistor that goes down to ground. We have a transistor which also goes to ground, and we have the RC resistor. So let's call that RC, let's call that R1, let's call that RP. So the input impedance is going to be a parallel combination of R1, RP, and some combination of the resistance over here. So Zin equals R1 in parallel with RP in parallel with RTEQ. Now RTEQ, which is basically, I'm calling this resistor over here, is going to be beta times RE. RE is the intrinsic emitter resistance over here, and beta we're going to assume equals 100, and beta is the current gain of the transistor. RE is equal to VT over IC. We know that the student has set RP so that this point over here is 10 volts. That means that there's 10 volts across RC, and RC is a 10 kilo ohm resistor. So IC is going to be equal to 10 volts divided by RC, which is equal to 1 milliamp. So then we have the value for this. VT is equal to 25 millivolts, and you can get that from the book. So then that gives us a RE value of 25 divided by 1, which is 25 ohms. Now if I multiply that by beta, we get RTEQ of 2500 ohms. So the only thing we need to calculate now is RP. To calculate RP, let's start off with an assumption that VBE is equal to 0.7 volts. So that's this voltage over here is 0.7 volts. So that means that we're going to have 0.7 volts on the base. So VB is equal to 0.7 volts. So we can calculate what we need RP to be, because we know what R1 is. VB is equal to VS, which is basically 20 volts, RP, R1 plus RP. So we need to rearrange this equation to get RP by itself. So VBR1 plus VBRP equals VSRP. Divide both sides by RP. So we get VBR1 RP plus VB equals VS VBR1 RP equals Vs minus Vb. Now if we divide both sides by VBR1, we get 1 over RP equals Vs minus Vb divided by VBR1. And then we just got to invert that. So that will give us RP is equal to VBR1 Vs minus Vb. So if we plug in those numbers, we get 0.7 times 1000 divided by 20 minus 0.7, which is equal to 36 ohms. So RP equals 36 ohms. So now we have this value and this value. We already knew the value of this resistor over here. We can calculate the input impedance. So Zin is equal to 1 over 1000 plus 1 over 36 plus 1 over 2500, which gives us a input impedance of 34 ohms. So you can see that input impedance is very low and is dominated by the potential divider that we have over here. And that is the solution for part A. Next, we're going to calculate the small signal gain of this amplifier circuit. So the gain AV is equal to RC divided by RE plus RE. Obviously, in our case, this value is equal to 0 as we don't have a resistor over here. And this resistor, we already calculated as being 25 ohms. So we can basically plug in these two numbers and get our gain. So RC is 10,000 ohms and RE is 25 ohms, which gives us a gain of minus 400. So we do need a minus sign over here as well. Now, lastly, we are going to calculate the temperature rise that will cause the transistor to saturate. Now, there are many ways of looking at this, but the simplest way I found is to look at a paragraph on page 125. So if I go to that paragraph, it basically says that the Ebers-Moll equation suggests that VBE at constant IC has a positive temperature coefficient because of the multiplying factor of T in VT. However, strong temperature dependence of IS, and this equation we can write down as IC is equal to IS EXP, exponential VBE VT. So what this part is saying that when IC is constant, typically VBE would have a positive temperature coefficient because of the multiplying factor of T in VT. However, this part of the equation has a strong temperature dependence and compensates for the positive temperature coefficient. Basically what that means in the end, and this is the only bit that you need to worry about, is that when the IC or the collector current is constant, we get a decrease in VBE voltage of minus 2.1 volts per degree C. Now, where this becomes useful to the question that we're trying to answer is the last part of the paragraph. So sometimes it's useful to cast this in terms of temperature dependence of IC at constant VBE. So in the case of the question that we're looking at, we are going to have a relatively constant VBE voltage because we've got a very stiff VB voltage over here. So the current flowing down this path is many milliamps. So if we calculate it, let's call this I1. So I1 is 20 divided by 1100, which gives us a current down this path of 18 milliamps, which obviously is a lot more than the current that we actually need to go down the base. So whatever increase in current you get over here is not going to result in a significant increase of current down this path. So this point over here is going to stay fixed at the 0.7 volts that we calculated. Obviously, this point over here is also fixed at ground. So our VBE voltage is fixed at 0.7 volts. Now, what this says after is that IC decreases about 9% per degree C. And it doubles for a change of 8 degrees of rise. So now we can use this part of this explanation to answer the question. So we know that we have 1 milliamp flowing down this path over here. Now, in order for the transistor to saturate, we need about 2 milliamps flowing down this path. So if there was 2 milliamps flowing down, basically all of the power supply voltage will drop across the resistor and there will be nothing left for the transistor. Now the typical transistor saturation voltage might be 0.2 to 0.4, but that's a relatively small number, so I'm going to ignore it. So what we need is about 2 milliamps flowing down this path for the transistor to saturate. So 2 milliamps, and the circuit is configured for 1 milliamp. So we basically need to double the amount of current that's flowing down this path for the transistor to saturate. And we already have the answer from the explanation, which is basically plus 8 degrees C of temperature rise. So that's the answer for part C of the question. But looking at it another way, we can also calculate it, which is basically so 8 degrees C of temperature rise will cause a doubling of IC current, which will cause the transistor to saturate. So that is the answer for part C of the question. Now this might be a little bit simplistic, but the other method, there is a lot of derivation and partial derivatives involved as well, which I don't think will bring much value. I think this rule of thumb that has been given to us by the book is useful for analyzing this type of question and this type of circuit. So hopefully you enjoyed this video. And finally, I want to say a big thanks to all the channel members. You make it so much easier for me to keep creating videos like this. If you'd like to support the channel and get involved too, consider becoming a member. It really helps keep these projects going. Thank you for watching. Bye for now.